These week 4 rigid body simulation videos were done before we had this nicer improved animation to work with, so I wanted to give you a quick update to show you some extra considerations when working with this new animation, and also just a few more ways to control your simulations and provide some extra features. So let's first take a look at what my first pass looks like. You see right here, I'm just focusing on getting a first pass at the tower portion in this movie. And so this is a good starting point. There are still some things that need to be fixed because, of course, this isn't colliding with the helipad at all. You'll see these pieces are going right through it, and obviously none of the helipad pieces are simulated at this point. But yeah, I just wanted to start with this tower to start getting that locked in. And I'll show you a few techniques that I use to help control that sim. So to start, I've copied over my proximity activation demo that we looked at in the earlier video. And I've wired in my new fractured geometry for the top of the tower. That's this here. And I've left our old attribute wrangle from that setup, which specifies a very late in time activation frame of 100,000, which means it never activates by default. And I've changed these initial velocities to 0 because at this point I don't want this to start out with initial velocity. I'll just let it use products of the collisions as a starting point, and then later on, if we want to kind of suggest it to move in certain areas or have a more obvious directional force, we can add that and that velocity in later for it to inherit. I also wanted to create a mass attribute that would be more useful to us. These pieces all have a volume associated with them because we're computing the volume in the fracture. And you'll notice if we sort by the volume primitive attribute, this has a really huge range. There are some pretty massive pieces in there, ranging from it looks like almost 10,000 down to super tiny. But I did notice some weirdness, which I should probably debug, but it looks like we're getting some negative volumes. And it seemed like those negative volumes are still valid values. It looks like their sign is flipped, so they should just be positive. So we're not doing a lot with the volume, and we're not doing anything with the volume sim-wise. It's mostly for calling out pieces and setting properties differently on the object. So this won't break things to have this negative volume right now. It's just something we'll need to watch out for. So I'm using that volume to create a mass attribute on each object. I'm promoting this volume primitive attribute to a point attribute using this attribute promote node. And by default, it has this box to delete the original ticked on. So that would delete the volume attribute, which I don't want it to do since I want to preserve that. So I make sure to not delete the original and use mass as the new name. And then I have a little attribute wrangle node here that is going to do a little tweak on that mass. So because some of the masses aren't in fact negative, I'm using this ABS function, which stands for absolute value, which will take all the negative values and make them positive. So to compute a new mass, I'm taking whichever is the maximum between the absolute value of the object or 1. So basically it'll take either the object's mass, or if it has a tiny mass, it will make it at least 1, just so we don't have any teeny tiny values for the mass on our objects. So now, if we display that attribute wrangle and look at the spreadsheet, and let's look at our point attributes. Now if we sort by mass, you'll see that we have mass values ranging from the super huge chunks with like almost 10,000 mass down through masses of 1 as the lowest value. Now some more of this setup will stay the same from our proximity triggering example. I've deleted out the attribute wrangle nodes that are setting different values for the right, left, and center chunks because we don't need to define different sections for what we're doing right now. But I've left on this active frame attribute creation, and we're still using the same solver that we used from the other example. The only small change I made to this solver is, well, let's see if we dive into it. I've pointed this object merge, which is pulling in a sphere before to compare proximity for the triggering of the objects. I'm now pointing that at a null node so that we can pipe anything we want into it and we don't have to keep changing that reference every time we use a different object. I made one other small change as well. The attribute transfer, I've just tweaked the distance a little bit. I think it used to be 50, I believe, and I'm now triggering objects within 60 units of the trigger object. So if we go out of the solver, you'll see this is where I've created this proximity activator null node, and I'm bringing in the robot's left shoulder as a reference object. So I'll display that. Now if I scrub the timeline, you can see we're reading in this shoulder object, and since that's connected to this null, which is being referenced by the solver, it'll use this shoulder for the proximity activation on these tower pieces, because it's kind of that left shoulder that's the leading portion of the robot. Now you may also want to use proximity triggering for some of the helipad stuff. I feel like this impact here might be better to be a hard-coded activation frame. Probably, since that's a very solid impact and all happening in one location, I think a hard-coded value with maybe a frame or two offset on the pieces randomly will work just fine there. But you may wish to use some proximity activation for when he slides across the helipad, since those sliding effects are a little bit trickier to key manually. But anyway, back to our tower building here. Let's look at what the activation looks like. Now I've added a delete node here to delete things once they become active. So if we start scrubbing through, you'll see that as soon as the robot comes near those pieces, they're activating. They're activating a bit ahead of the robot because this robot's moving really fast. And you'll notice from here to here, he's already intersecting over that one frame difference. He's driving into the object quite a bit. So we want to make sure that these objects are activated at least one frame ahead of where they're actually colliding. And those objects shouldn't move too much when they first activate, so your collision timing should still look nice even if they activate a frame early. Now this switch node I've added is just mainly for display purposes. If we visualize the solver, you'll notice that before frame 1019, which is the start frame of that solver, it doesn't output any geometry. So if I keep stepping through, it doesn't show up until it hits frame 1019. But I wanted there to be some geometry in this network at all times. So I'm using the switch statement, which is checking the start frame of our DOPNet, and it's checking to see if the current frame is less than that. So if the current frame is less than that, from 1000 to 1018, then it's instead going to pass along our original geometry here, instead of the solver output, which is once again calculating our active frame. Now let's take a look at our collision geometry. So I have two sections of collision geometry here. One of them is static geometry that isn't animated, and the other is for animated geo. So for the static collision geometry, I'm bringing in just this tower portion right now, just the broken pieces from our fracture that we don't want to have in motion. And this is just a quick temporary first pass, so there will certainly be more objects that we'll want to add in here. For example, we'll probably need to add in these levels here of that tower and some of the helipad stuff, and that'll probably do it for the static non-animated colliders. Depending on what your scene looks like, you may have other things. And then in addition to this static collision null, we have another object merge for the animated pieces of geometry. So for this, I've brought in just a few pieces of the robot to start with. He's tumbling through the debris quite a bit, so we'll probably need to add in his legs as well. It's always good to use as few colliders as possible. For example, we probably don't need to collide with his fingers. Things are so chaotic and motion blurred that even if something intersects his finger a little bit, it's probably not going to be a very big deal, and you're probably not going to notice it. So I would try to limit your colliders to only the stuff that you really need. So I just started with these objects, and in this object merge node, you'll see that you can add as many fields as you want to bring in as many objects as you need to. In this case, I'm using 12 pieces of that robot. And because that robot alembic node has a transform on it to bring it, to scale it down to 10% of its size to put it in the right space for the shot, we need to flip this transform option into this object in order for that to be in the right space. Now you'll also notice that I added a time blend node here. Now we may or may not need this depending on our animated geometry input. In this particular case, as I look at it more closely, I'm turning off this integer frame values and our timeline options here, which means I can scrub on subframes, and it looks like the way that it's bringing in the animation with actual anim curves on the object, that oh, it looks like we have some subframe weirdness. Hopefully that won't break anything. We can cross that bridge if it becomes a problem later. But you'll see that this is actually interpolating the animation. There are some cases where it won't interpolate smoothly. It'll jump from frame to frame, and the subframes won't be nicely interpolated like that. So in those cases, you would need to use a time blend. I often drop it in just to be safe, but yeah, it looks like this time we don't actually need it. Not that it's hurting us at all. But anyway, this is piped into a null node for our animated collision geometry. Actually, before we continue on, let's take a look at the interpolation of the original animation versus the time blended animation. So if we once again turn off our integer frame value scrubbing, you'll see it's freaking out between 119 and 120, for example. But then if we visualize our time blend, it looks like that's actually fixing a lot of those in-between interpolation issues, because this time blend is calculating the position. For example, in this case, we're at frame 1019.17. So this time blend node will look at frame 1019 and 1020, and it'll find how far it is between them, and will blend between those two positions. So in this case, it's actually, it appears to be saving us those interpolation problems. I don't know that this would really break things badly if we ran the simulation with those subframe issues, but it is possible that could create some weirdness on our collisions. So this time blend is actually quite beneficial in this case, even though we do have subframe data on our animation. Now let's turn our integer frame scrubbing back on and take a look at how these colliders are added to our DOP simulation. So before we dive into the DOPNet, we should also note that I've turned my substeps up from 1 to 4, once again because this robot is flying through space pretty quick. Turning this up to 4 means that it will evaluate the simulation 4 times per frame instead of just once per frame, and it can help you handle some fast-moving objects, and it will also increase the accuracy of your simulation. Of course, it'll take longer, but the sim that we're working with here isn't very heavy at this point, so it's really not hurting us much to turn it up to 4. So if we dive inside this DOPNet here, let's take a look at how those static colliders are added. So here I've created a static object node for the robot and another one for the static geometry. We might be able to wire them into the same merge node, but I tend to use separate merge nodes, and I know it works this way. Not sure if it works the other way. But in any case, for this static object for the robot, we'll point the SOP path to our animated collision null node, and we'll have to turn on use deforming geometry for that. And a similar thing for the static geometry, pointed at that null node, except we don't have deforming geometry on here. And for both of these, I've changed the values initially. So I set the bounce on them to 0. So this is a very high velocity impact. This robot is really slamming into this stuff hard. And I know from working on these kinds of scenarios that things can really start exploding all over the place pretty violently. So I am just starting with no bounce on these objects, just to start with a pretty highly controlled simulation. And I've left the friction on for the static objects, but for the robot colliders, I've turned that down to 0.5, just to once again, to tame that collision impact a little bit, and to, reducing the friction on it, I feel will probably make it slide through the geometry a little bit better and keep it from making pieces fly around quite as violently. And we can always tweak that later as we need to, but that seemed like a sensible starting point. And I've also, on this RBD packed object, I've reduced the bounce to 0 as a starting point as well, and turned the friction down to 0.5. And the other change I've made on this packed object is, if you remember, we calculated a mass attribute earlier, and it's a point attribute on our input geometry, but we have to specify the mass here and the overwritten attributes so that it reads that from our input geometry. Now, if we dive back out of our DOPNet, and I've added a switch node here, similarly to how I've added a switch node after the solver, so that it shows our input geo prior to our simulation start frame. I've just copied that switch statement down here so that we can see something before the simulation starts. Because if we just view the DOPNet, very similarly to our active frame solver, there's nothing that shows up until we hit that simulation start frame. So it's nice for play blasting your work and such to have that geometry displayed before the sim as well. So let's show all of our objects and look at this from the camera view, and then let's see what our simulation looks like at this point. Now you'll see this is running pretty quickly. I haven't sped this footage up at all. This is the actual real-time evaluation of the sim. So even though we have a fair amount of geometry, it's really not too bad to simulate this, even with our animated collision geo. But you'll see this is pretty crazy impact right now. Especially when we're working at such a massive scale with such a huge skyscraper. It doesn't seem like things should spew out this far from the initial impact, and it's a pretty uncontrolled simulation at this point. It's a bit too wild, and you can see how it makes sense to start with a really low bounce value, because even though we have a bounce at 0 for everything, it's still pretty intense and things are really flying pretty out of control right now. So in order to tame this, I made a few changes to my sim. Let's go back to the start frame. So for one, I've added some drag force here. I'll turn that back on. And I've increased the gravity up to 20 times negative 9.8. Because it seems like things are kind of hovering a bit too much and we want them to fall a bit faster. And then the really key change that I've made here is on this attribute wrangle pre-sim node. So if you remember from our other activation demos this week, this is kind of a catch-all attribute wrangle node that we can put extra code into to modify attributes and such before the simulation. It does a whole bunch of things. We've been using it to add offsets to our active frame. Right now it's using offsets of 0, but it does things like set the active value of the object based on the active frame, and this is a sensible place for us to add a speed limit for our pieces. So this is a scenario where it's good to take the mass of the object into account. So typically, I expect the smaller pieces to spray out further and more easily than the big pieces. I think the big pieces should resist being thrust about and they shouldn't go quite as far. So we can use a speed max and a spin max parameter to control the maximum speeds based on the mass of the object. So if we look at the spreadsheet for this geometry and we look at these mass values, let's sort that. And we'll see that our masses range from 1 and it goes up pretty steadily until we reach around, looks like around 200. There's a drastic jump up to 500 and it shoots up pretty wildly from there. So we can use a range of, let's say, everything with a mass of 5 or less gets one value, and everything with a mass of 500 or more gets another value, and then we can have that blend between the two. So I believe we've already looked at using a fit function. So we can use a line of code that says this attribute speed max equals a fit function, which we're passing in the mass as the first input. And then the second and third inputs are the minimum and maximum mass values. So this isn't the actual min and max and as far as the actual values on the object. These are the ones that we want to consider for our minimum and maximum speeds. So these last two values will be the speeds associated with the two masses. So a mass of 5, in this case, will get a speed limit of 200, and a mass of 500 will get a speed limit of 100. So this is an actual speed amount, not an amount that it's dampening it by. So basically the small pieces are allowed to be twice as fast as the really large pieces. And we're doing a similar thing on the spin max, except we're allowing the small pieces to have a spin of 10 and the large pieces to have a spin of 5. So now let's once again look at our DOPNet and rewind our sim, and let's play through this here. And now we should see that these large pieces don't fly out quite as far as the small ones do. The entire simulation is much more contained. It's not flying out nearly as far to screen left because that made things feel really far too lightweight and not realistic. And this much more contained simulation feels a lot more realistic and believable. So yeah, this speed max and spin max is a really super handy way to control your pieces and vary it by their size. Very, very handy option. And yeah, this is pretty much the core of how I've accomplished my first pass at this rigid simulation. For this week, I'd also like you to add in the impact when he first hits the helipad and shoot up some pieces when he scrapes across it. I don't expect it to be a perfect simulation, of course, for this first pass. But yeah, try to block in all of those elements. For some of these pieces, you might want to use some of the initial velocity techniques that we've looked at this week. For example, this initial impact here, it would be good to get some radial force to these pieces. So you could, for example, use the reference point technique, where you use a reference point kind of below the object a little bit and at the center of the impact, so that when it computes the velocity vectors, it kind of sprays out in a radial fashion. For the pieces that get kicked up when he slides across it, that might be a better case for you to select some groups of those pieces by hand and specify a hard-coded velocity in either direction, maybe with some randomized offsets to that velocity. And yeah, play around with the techniques a bit, and let's try to get as far as we can with the different elements in here. I know it's kind of a lot to tackle a few different sections, but take it as far as you can, and we'll continue to develop this over the next few weeks.